Most people hate statistics and they would rather have nothing to do with it. Nevertheless, many healthcare practitioners need to know statistics either for research or to understand scientific publications. I am Oluwadiya Kehinde. This is the third of a three-part lecture on using advanced statistical methods for medical research. In the first part, I showed that it is in your best interest to get to grip with statistics by demonstrating that many research papers are full of errors, and you need to be able to spot errors in published studies. In addition, I also showed you the three most important functions of statistics. Finally, I showed you why you may need to transform the variables in your data. I ended the first lecture by demonstrating how to do logarithmic transformation in SPSS. In the second lecture in the series, we looked at the limitations of the p-value. We also looked at some statistical methods for comparing two or more groups when the data is continuous. We ended the second lecture by digging into regression and correlation. In this, the third and final lecture in the series, we will be treating the 5 topics highlighted on the slide. We will start with factorial and covariate designs, go on to risk and odds ratio, touch on survival analysis, sensitivity, specificity, and ROC curves. We will end the series by looking at how you can determine the right statistical tests for any given data. In this, the first section of the lecture, we will be covering factorial and covariate designs, which are the first objectives of this lecture. What is a factorial design? A factorial design is an experimental study in which the study has more than one independent variable and independent variables are categorical. For example, a researcher might want to investigate the effects of gender and social status on the outcome of a disease such as tuberculosis. Factors are the categorical independent variables that the researcher introduced into the experiment to study their effects on the dependent variable. Gender and economic status are the factors in the example given on this slide. What is a factor? Factors are categorical. A factor has 2 or more categories. For example, gender has 2 categories, which can be male or female. And social status may have 3 categories, which can be upper, middle, or lower class. What is the accepted way of presenting factorial designs in articles, presentations, and documents? The widely accepted format is the multiplication notation as shown. For example, we can have a 3x4 notation or a 4x3x2 notation. How can you explain the multiplication notation? The multiplication notation can be explained in the following ways. Take a 3x4 notation for example. How many numbers do you have in the multiplication? In this case, there are just 2, 3 and 4. Therefore, there are 2 factors in the study. How can you explain the categories of each factor from the multiplication notation? This too is easy to know once you can recognize the clues. Again, let's look at the 3x4 design example. How many categories are in each of the 2 factors? That can be recognized from the value of each factor. Therefore, the first factor has 3 levels and the second has 4 levels. Just to be sure you understand multiplication notation of factorial design, why don't you pause the video and take a moment to answer the questions on the screen? Here are the answers to the quiz. Again, you may pause the video to go through the explanations. Once you do the analysis of the data obtained from a factorial design, 2 types of effects of the independent variable on the dependent variable are possible. The first is the main effect. This is the effect of one independent variable on the dependent variable, ignoring the effects of all other independent variables. This is similar to the result one would have obtained in a one-way ANOVA. The second is the interaction effect. This is the effect of one independent variable on the dependent variable while taking the effect of the other independent variables into consideration. The interactive effect is the reason why investigators go through the trouble of doing a multifactorial analysis rather than a simple one-level analysis. This slide shows the result of a study in which the effect of an analgesic drug and physiotherapy on back pain in a group of patients was investigated. The two treatments are the factors. Remember that factors are the independent variable. In the graph, the two groups of drug, which is one of the two independent variables, is on the x-axis. The two groups of physiotherapy, the other independent variable, are represented by the two slopes in the graph. The dependent variable is the patient's evaluation of their back pain symptoms using the visual analog scale, VAS. Lower scores indicate better pain control. Therefore, a patient with a VAS score of 2 has a less severe pain than a patient who scores 7. The dependent variable is on the y-axis. The patients were divided into 4 groups based on the treatment they received. Group 1 took drug alone. Group 2 were on physiotherapy alone. Group 3 were on both drug and physiotherapy, while Group 4 received no treatment at all. It is the control group. What can we observe in the graph? The two lines are not parallel, meaning there's an interactive effect. An interactive effect is indicated when the two lines representing the second independent variable are not parallel. Secondly, the difference between the drug and no drug group was greater for no physiotherapy than for physiotherapy subjects. For example, the patients who had no physiotherapy when given drug has a VAS score of 2, and when they had no drug has a VAS score of 7. Whereas those who were given physiotherapy had the VAS score of 1 when they had drug along with the physiotherapy, and the VAS score of 3 when they were not given any physiotherapy. Thirdly, there was a greater difference between physiotherapy and no physiotherapy for subjects in the no drug group than there was for subjects in the drug group, as seen here. This is the difference between no physiotherapy and physiotherapy when patients was given drugs. Whereas for no drug group, the difference is much wider. So what would be our conclusion from our observation? The first conclusion is that the patients who received a combination of both treatments had better pain control. That is the point labeled 3 on the graph. Number 2, drug on its own appears to be more effective than physiotherapy alone. Patients who received drugs alone had a VAS score of 2, whereas patients who had physiotherapy alone had a VAS score of 3. Finally, as expected, patients who received no treatment performed most poorly, as shown on the graph. In the previous slides, we learned that a factorial ANOVA is used for situations where you want to investigate the effect of 2 or more categorical factors on the dependent variable. What about situations when you want to investigate the effects of a categorical and a continuous variable on the dependent variable? That is when you should use a covariate design. Covariate designs are used when the subjects differ because of the influence of a continuous variable. Covariates are the continuous variables you adjust for in your research. For instance, if you are testing a new drug for the treatment of hypertension, you might want to see how social status affects blood pressure. But knowing that the weight of a patient will affect their blood pressure, you can measure the weight of the patients and use the continuous variable as a covariate in the subsequent analysis that will take the weight of the patients into account. So what statistical method do you use for analyzing covariate designs? ANCOVA is used. ANCOVA is similar to ANOVA. The obvious difference is the C in ANCOVA, which stands for covariance. Like ANOVA, ANCOVA has a single continuous dependent variable. Unlike ANOVA, ANCOVA looks for the effect of both a factor and a continuous independent variable on the dependent variable. The covariance is measured before the interventions are applied, and during statistical analysis, the difference caused by the covariate will be accounted for. What are the requirements of ANCOVA? You need at least 3 variables. One categorical independent variable with 2 or more levels, e.g. social status. This is the factor. One or more continuous independent variable, e.g. maternal blood sugar. This is the covariate. And finally, a continuous dependent variable, for example, birth weight. We have come to the second section. Here, we will be discussing risks and odds in statistics. What do you mean by risk? In lay terms, risk is generally associated with a bad event, but risk in statistical terms is not necessarily a bad thing. It simply refers to the probability that an event will occur, whether it be a good or bad event. Risk is the probability that an event will happen. Risk is the number of events divided by the number of people at risk. Now, let's look at an example. You have 124 smokers, and over a 5-year period, 5 of them develops lung cancer. What is the probability of a smoker in that group developing lung cancer? That would be 5 divided by 124, which is 0.04. You will then multiply 0.04 by 100 to obtain the percentage and report the risk as 4%. To compare two risks, just divide one by the other to obtain a ratio called the relative risk. For example, you could divide the risk of cancer among smokers by the risk of cancer among non-smokers to obtain the relative risk of cancer among smokers. Please note that relative risk and risk ratio means the same thing, but relative risk is a more commonly used term than risk ratio. How is relative risk calculated? In a group of 500 people made up of 124 smokers and 376 non-smokers, if after 5 years, 5 smokers and 3 non-smokers develop lung cancers, what will be the relative risk of smokers developing lung cancer compared to non-smoker? Risk of cancer among smokers is 5 divided by 124, which will give you 0.04. Risk of cancer among non-smokers is 3 divided by 376, which will give you 0.008. Therefore, relative risk of cancer among smokers compared to non-smokers will be 0.04 divided by 0.008, which is equal to 5. How do you interpret relative risk? Relative risk always starts from 0. A relative risk of 1.0 means that the risk of the event is identical in the exposed and control samples, whereas a relative risk that is less than 1.0 means that the risk is lower in the exposed sample, while a relative risk that is greater than 1.0 means that the risk is increased in the exposed sample. Relative risk is widely used in medical research. Relative risks are used to compare risks in 2 types of studies. In cohort studies, where you know the incidence of the disease, and in cross-sectional studies, because you know the prevalence. What is a cohort? In statistics, a cohort is a group of persons who experience a certain event in a specified period of time. In cohort studies, you divide the cohort into groups based on exposure to the risk factors you are interested in. You then follow up the cohort over a certain period to see whether the group members experience the event. In our previous example, the exposure is smoking, and on this basis, you divide the cohort into smokers and non-smokers. The event of interest was lung cancer. What if, like in case control studies, you neither know the prevalence nor the incidence of the disease? What is an odd? An odd is another way of measuring probability. It is useful when we don't have the incidence or prevalence of an event, and yet we want to know the probability of the event happening. A classic example are case control studies. In case control studies, the prevalence stroke incidence of a disease is unknown because the groups in the study are matched based on some characteristics. And odd is the probability of an event happening divided by the probability of an event not happening. Now, let's calculate the odds of lung cancer among smokers using the data we used to calculate risk. You have 124 smokers, and over a 5-year period, 5 of them develops lung cancer. What are the odds of a smoker developing lung cancer? If 5 out of 124 smokers had lung cancer, it means that 119 people did not develop lung cancer. Therefore, the odds of developing lung cancer are 5 divided by 119, which is 0.042. You will then multiply 0.042 by 100 to obtain the percentage and report the risk as 4.2%. To compare two odds, just divide one by the other to obtain a ratio called the odds ratio. For example, you could divide the odds of cancer among smokers by the odds of cancer among non-smokers to obtain the odds ratio of cancer among smokers. Using the lung cancer data, let's calculate the odds ratio for cancer among smokers compared to non-smokers. For reasons mentioned earlier, relative risk cannot be used for calculating the probability of an event in case control studies. Can you still remember this reason? To calculate odds ratio, just divide the odds of one event with the odds of the other event. In a case control study where 124 smokers were matched with 396 non-smokers, 5 and 3 participants from smokers and non-smokers developed lung cancers respectively. Odds of a cancer among smokers is 5 divided by 119, which is 0.04. Odds of cancer among non-smokers is 3 divided by 373, which is equal to 0.008. Odds ratio of lung cancer among smokers compared to non-smokers is 0.042 divided by 0.0084, which is 5.25. This is slightly higher than the relative risk of 5.0 obtained using the same pool of data. So, odds ratio and relative risks are not always the same. That is the lesson to learn. Odds ratio are mostly used when it is not possible to calculate risk. Odds ratio are also generated as a result of certain complex statistics like logistic regressions. So, what is the relationship between odds ratio and relative risk? Relative risk and odds ratio are not equivalent, even though they are often interpreted as such by many in medical literature. For example, a relative risk of 2 means a twofold increase in probability of the event happening compared to the non-event, whereas an odds ratio of 2 does not mean the same thing. An odds ratio of 2 means the odds of an event happening is 2 times the odds of the event not happening. Subtle, but the difference is there. In addition, you should also note that odds ratio are always higher than relative risk, because odds ratios tend to overestimate risks. If 5 out of 100 people develop an event, the relative risk is 0.05 and the odds ratio is 0.526. The odds ratio is just 5.2% higher than the relative risk. This means that when the event is rare, both the relative risk and the odds ratio are very close and can be approximated. But as the event becomes more common, this will change. Watch what happens when 30 events happened. The relative risk is now 0.3 and the odds ratio is now 0.43. This is a 43.3% difference. We can no longer approximate the two. But wait, worse is yet to come. What if the event happens 50 times? The risk becomes 0.50 and the odds ratios has risen to 1. A 100% difference. This graph shows the relationship between risks and odds as the prevalence increases. The odds ratio is on the y-axis while the relative risk is on the x-axis. The curves represent the prevalence of the events. To illustrate the point we are making, I will show the equivalent odd ratios for a relative risk of 5 as the prevalence increases. When the prevalence is 0.01, the odds ratio is slightly greater than 5. When the prevalence is 0.05, the odds ratio has risen to 6. And when the prevalence is 0.1, the odds ratio is almost 9. The important take-home message is that when you are dealing with common events, be very mindful of the probability measure you choose to use. This slide shows some terms that are used to describe risks and changes in risks. We will be digging into the nitty-gritty of these terms in future videos in the series. This section covers survivor analysis, which is the third of our objectives. Survivor analysis is also known as time-to-event analysis. We use survivor analysis to study the amount of time it takes before a particular event of interest occurs. There are other more common statistical methods that we may use to determine how long it could take for something to happen. For example, linear and logistic regression analysis are commonly used to determine how specific factors such as smoking, obesity, and diets might help to predict survival times. The problem is that linear and logistic regressions are not able to account for censoring. We will be taking a closer look at censoring later in the lecture. Survivor analysis is also versatile as it can not only compare survivor between two groups, for example, between cases and controls, it can also assess how various factors called covariates can affect survivor time. What do you need to do a survivor analysis? First, you need to know what you want to study. What is your outcome variable? Is it death or the development of a complication such as recurrence? Secondly, you must specify the start and end time of the study observation period. Therefore, survivor analysis always takes place within specific span of time, which are determined at the onset. Finally, the end point, which is either the time taken for subjects to experience the event or the time to censoring for each subject, is determined. In a study where the outcome is death, 3 outcomes are possible. A patient may die from disease, which is the event. The patient can also still be alive at the end of the study, or the patient may not complete the study. The last 2 cases are examples of censored data. So what is censored data? I will illustrate the concept of censoring with the graph that we've shown before. Data can become censored in 4 possible ways. 1, event did not occur by the end of the study. 2, subject died from an unrelated cause. Subject is lost to follow-up. And subjects withdrew from the study. When is it better to use survivor analysis instead of other methods of estimating factors that will affect outcome? The first of those instances is when the researcher wants to estimate time to event for a group of individuals. For example, you might want to estimate the time to death in a group of patients with cancer of the lung. On the other hand, you might also want to compare time to event between 2 or more groups. You might also want to compare, for example, survival time between lung cancer patients treated with surgery to those treated with a combination of surgery and chemotherapy. Finally, you might want to assess the effects or factors on survival time. For example, you might want to investigate how weight, smoking, or cholesterol influence survival time of patients with myocardial infarction. Survivor analysis are a group of statistical methods which include Kaplan-Meier curves, hazard ratios, and Cox regression hazards. This slide shows an example of Kaplan-Meier curves. The graph shows how you can use Kaplan-Meier curves to compare the survival of 2 groups. Here we are comparing the survival times of males and females who had cancer of the lung. On this slide, we have blown up the graph so we can look at the different parts of a typical survival curve. Events on survival curves are represented by steps, while censored cases are represented by ticks. Kaplan-Meier curves provide a graphical means of comparing the outcomes of 2 groups. For example, the control group has a higher survival than the treatment group. Also, survival times can be measured directly from the curve. For example, the median survival time of treated group is 60 days and 125 days for the control group. But Kaplan-Meier curve has a weakness. It does not account for confounding or the effects of other covariates on survival times. How will you do Kaplan-Meier survival analysis in SPSS? Click on Analyze in the menu bar, then click on Survival and then on Kaplan-Meier. Cox regression model is commonly used in long-term studies where various factors called covariates might predispose to an event. Example, you might want to find out which factors like age, race, tumor staging might make recurrence more likely after radiotherapy. Since it is a form of regression, it means you can infer causality from it. The result of the analysis is reported as hazard ratios, which are interpreted in a similar fashion to relative risks and odds ratio. Hazard ratio of 1 means there's no effect. Hazard ratio greater than 1 means there is an increased risk, and hazard ratios less than 1 means there is a decreased risk. In this section, we shall be looking at sensitivity and specificity, which are the 4th objectives of the lecture. Sensitivity and specificity are terms used to evaluate a clinical test. They are used when you want to compare a new diagnostic or screening test to an established test that is usually referred to as the gold standard. What is sensitivity? Sensitivity is the ability of a test to identify correctly individuals who are affected by the disease. It is the proportion of people testing positive among affected individuals. The table is the standard format of representing the data for calculating sensitivity and specificity of a test, be it diagnostic or for screening. The risk status of the patients is presented in the columns. This is the status as defined by the gold standard. The rows represent the performance of the diagnostic test that is being evaluated. Any patient can have just one of 4 expected outcomes, which corresponds to the 4 cells in the table. Cell A contains the total number of those who have the disease and are found to be positive by the diagnostic test. These are the true positives. Cell B is for those who do not have the disease but are found to be positive by the diagnostic test. These are the false positive. Cell C is for those who have the disease but are found to be negative by the test. These are the false negatives. And cell D contains the number of those who do not have the disease and are found to be so by the test. These are the true negatives. To calculate sensitivity, divide the true positive A by the total number of those who truly have the disease, which is A plus C. Now, let's talk about specificity. It is the ability of a test to identify correctly individuals who are not affected. In other words, it is the proportion of people testing negative among non-affected individuals. In the notation table, you divide the true negative D by the total number of those who do not have the disease, B plus D. The same formula in the previous slides can be represented in the form shown on this slide, where the alphabetic notations have been replaced by descriptive notation in the form of true and false positive and false and true negatives. However, only the notations has changed. The underlying meanings are still the same. In an ideal world, a diagnostic test will clearly distinguish between those who have the disease and those who do not. In other words, a graph of the performance of the test will show the true negatives clearly separated from the true positives with no overlap. Alas, reality is messy. Diagnostic tests will always have overlapping true positive and true negatives. In this example, we can see that the threshold has cut into those who have the disease as well as those who do not. This has produced the false negative and the false positive nests. The position of the threshold is therefore very important, as this will determine the relative proportion of false negative, false positive, and true positive. Let's see what will happen if we decide to lower the threshold by shifting the threshold to the left. False negative has gone down, while true positive have gone up. At the same time, the false positives have gone up while the true negatives have gone down, which means that sensitivity has moved up at the expense of specificity, which has gone down. What if you move the threshold up? False positive has gone down, while false negative has gone up. Similarly, true negative has gone up, while false positive has gone down, which means that specificity has moved up at the expense of sensitivity, which has gone down. Shifting the threshold has opposite effects on sensitivity and specificity. It comes at a cost, and you must make compromises. Are you prepared to have a false positive, or will you rather have more of false negatives? Let's look at the following example. In the screening test for congenital toxoplasmosis, which one would you rather have? Reduce the threshold to increase sensitivity, which means you will capture more of the cases with the disease, but at the expense of increasing the number of those who do not have the disease but are identified as positive by the test. In other words, you increase the true positive while you also increase the false positive. Since we know the earlier the treatment for congenital toxoplasmosis is started, the better the prognosis. So it is important to identify all cases, even if the probability of including some normal cases is increased as false positive. Making this decision is made easier because the treatment is not expensive and is also relatively safe. So the potential complications of giving unnecessary treatment to the false positive cases is not very great. On the other hand, you should prioritize specificity whenever you are dealing with a relatively non-life-threatening disease with expensive or complicated treatment schedule. In this instance, you want to make sure that you minimize false positive rates. Two mnemonics have been developed to make it easy for physicians to use specificity and sensitivity to confirm diseases with diagnostic tests that have high sensitivity or specificity. The first is SNOUT, S-N-N-O-U-T, which means high sensitivity negative rules out. A highly sensitive test can be useful for ruling out a disease if a person has a negative result. For example, a negative result on a pap smear probably means the person does not have cervical cancer. The second is SPIN, S-P-P-I-N, high specificity positive rules in. Tests with a high specificity are most useful when the result is positive. A highly specific test can be useful for ruling in patients who have a certain disease. The ROC curve is a plot of the values of sensitivity versus 1 minus specificity. The ROC curve on the right is generated from the Mayo dataset from the EASY ROC website. Sensitivity, or the true positive rate, is plotted on the y-axis, while 1 minus specificity, or the false positive rate, is plotted on the x-axis. Each point on the curve represents a cutoff point for sensitivity and specificity. It has the advantage over ordinary sensitivity and specificity in the sense that you can compare the performance of a multiple tests using ROC curve. Let's use this graph to quickly look at the uses of ROC curve. First, you can identify the test with the best performance. Two methods are available for identifying the model with the best performance. The first method is by identifying the curve that sits close to the upper left hand corner. A model with high sensitivity and high specificity will have a ROC curve that hugs the upper left corner. So in this example, for example, the Mayo score is closest to this upper left hand corner. Such a model will be doing a good job of discriminating between those who have the disease and those who do not. A model with low sensitivity and low specificity will have a curve that is close to the 45-degree diagonal line. The 45-degree diagonal line is the line of no effect. So what we can see here is that as far as these two curves are concerned, Mayo score 4 is doing a better job at discriminating than Mayo score 5 because it is closer to the upper left hand corner. The second method is by using the area under the curve. The area under the curve of a particular curve is the part covered by that curve. So for example, the area under the curve for Mayo score 5 is this area, while the area under the curve for Mayo score 4 is all these areas. So looking at this, we should be able to deduct that the area under the curve for Mayo score 4 is actually higher than the area under the curve for Mayo score 5. So based on this, we can come to the conclusion that Mayo score 4 is a better classifier than Mayo score 5. The second use of the ROC curve is that it helps to determine the optimal cutoff point for each classifier. The optimal cutoff point is the threshold which combines the highest true positive rate with the lowest false positive rate. This can relieve clinicians of the burden of having to determine the cutoff point, as it is the case with using sensitivity and specificity alone. Here is an example from a real-life study which compares the utility of 4 trauma score measures in classifying trauma patients into those who will need admission in the casualty and those who can be discharged home. KTS, which is Kampala Trauma Score, is the best classifier for this because it is closest to the left upper hand corner. This slide shows one of the tables produced from the ROC procedure in SPSS. The table shows the AUC, area under the curve, for each of the classifiers in the second column. It is immediately obvious that the KTS has the highest area under the curve. This tallies with the ROC curve as seen on the previous slide. The table also provides us with an optimal cutoff point for discriminating between those who will need admission for each of the 4 trauma scores. Thus, the optimal cutoff point for KTS is 12. This point has a sensitivity of 100% and a specificity of 70% for identifying trauma patients who will need admission casualty. This slide shows the procedure for doing ROC curve in SPSS. You click on Analyze, then ROC curves. For most people, especially those who are new to statistics, knowing the correct statistical method to use for analyzing their data can be very difficult. In this, the final section of the lecture, we shall be looking at the guidelines to guide you in choosing the right statistics for analyzing the data you have. Please note that the guidelines in this section is not comprehensive. It will be limited to descriptive statistics, hypothesis tests of differences, correlations, and regressions. This slide shows the statistical analysis of the methodology section of a real research proposal submitted by a resident doctor for a project. Let's fish through it for the mistakes it contains. My comments on the mistakes are contained in the callouts. The resident wrote that data will be analyzed using SPSS 15. Univariate analysis will be conducted for the association of outcomes variables with other characteristics. My comment on that is that tests of associations are not univariate analysis. Chi-square test for significance will be used for categorical variables. T-test for parametric and Wilcoxon rank sum test for non-parametric variables. My comment on that is that Wilcoxon rank test, yes, it is a parametric technique, but it is used for paired sampling. He went on, multivariate analysis using either linear or logistic regression or correlations will be conducted for characteristics like age, experience, and alcohol/herbal mixture use. Regressions are not conducted for individual variables. They are used for building models to determine causes and effects. He concluded the level of significance will be 0.05, while 95% confidence intervals of estimates of the outcomes variables will be calculated. Wow, got no comment for that. So, how do you select the right descriptive statistics for your study? For categorical variable, this is a no-brainer because frequency analysis is sufficient for most cases. However, things are a bit more varied for continuous variables. Descriptive statistics for continuous variables are basically of two types: measure of central tendencies and measure of dispersion. The most important question you should consider when it comes to deciding on the descriptive statistics to use is the distribution of the variable in question. The flow chart provides a good guide. The distribution can either be normal or non-normal. For normal distribution, the measure of central tendency to use is the normal, and the measure of dispersion to use is the standard deviation. For the non-normal data, please use the median as the measure of central tendency and the range or the interquartile range as the measure of dispersion. Let us consider inferential statistics. How do you select the correct inferential statistics? The first thing you need to look at is the kind of variable you are dealing with. In general, all quantitative variables can be divided into numeric variable, ordinal variable, and nominal or categorical variable. Then you should ask about the distribution of the dependent variable. Many parametric tests have non-parametric equivalents. The non-parametric equivalent of t-test is the man with mu, and the non-parametric equivalent of ANOVA, for example, is the Kruskal-Wallis test. Next, you should look at the number of categories in the independent variable. How many groups are in the independent variable? For parametric tests, you should use t-test when the independent variables has only 2 categories. Use ANOVA when it has 3 or more categories. For non-parametric, use man with mu, which is the non-parametric equivalent of t-test when the independent variable has only 2 categories. And you should use Kruskal-Wallis, the non-parametric equivalent of ANOVA, when the independent variable has 3 or more categories. Then you should consider if you are dealing with a before and after study in which measurements are taken more than one time from each participant in the study. This design, also called the crossover design, will violate the assumption of independence in t-test and ANOVA. For studies of this type, you should use the paired t-test in place of the t-test and repeated measure ANOVA in place of one-way ANOVA. When the outcome of interest is the time to an event and there are possibilities of censoring, then consider survivor analysis. This table summarizes the guidelines for you. We have come to the end of the final part of the lecture series. In this lecture, we have covered risk ratios and odds ratio, survivor analysis, sensitivity, specificity, and ROC curves. We ended the lectures by looking at the guidelines for choosing the right test for specific data sets. I am Oluwadiya Kehinde, a professor of orthopedic and traumatology at the Ekiti State University, Ado-Ekiti, in Ekiti State, Nigeria. I have been teaching SPSS in healthcare research since 2004 in Nigeria and South Africa. I'm also the author of the best-selling book on SPSS in Nigeria, Getting to Know SPSS, which also have supplementary chapters on online literature search, as well as Zotero and EndNote reference manager software. I am also the CEO of Post Educational Consult, which specializes in training in statistical software and health education. My website is at www.oluwadiya.com. Check it out for more information on my book. The website also contains close to 50 downloadable PDF copies of my lectures in anatomy and orthopedics. Finally, you'll come across assorted information on medical practice in Nigeria. Please subscribe to my YouTube channel at the address shown. This is the third item I have uploaded. In the next few weeks, I am going to add other uploads at the rate of 1 to 2 per week. The uploads will cover all my courses at both undergraduate and postgraduate levels eventually. These courses include anatomy, orthopedics, and traumatology, SPSS, and general statistics. Stay along with me, the best is yet to come. Thank you for your time and attention, and as they say in my language, ẹ ṣeun.